Okay, so yeah, last time we were talking about unification. Yeah, I was talking about it in the context of first order resolution. They're in a bad shape. Yeah. Now, in general, if you have got two clauses alpha beta and not beta gamma, you resolve and you get alpha or gamma. And this is basically the soundness of the identity alpha or beta and not beta or gamma is equivalent to alpha or gamma. Yeah, this is the propositional identity, and this is what is used for resolution. So, if you want refutation by resolution, for refutation, you want to prove something, you start with the negation of that formula. So, negate the goal formula, convert to CNF, conjunctive normal form, really, I'll keep trying all the pens until I find one. And this is the notation. So, you have clauses C1, C2, Cm standing for conjunction C1 and C2 and Cm, and each Ci is alpha I1 or alpha Ik written in this notation alpha Ik, and these are supposed to be in negation normal form, that is negations pushed. Yeah. So, negations are pushed inside. So, what you have finally are literals. So, these are all literals. Yeah. And so, atomic formulas are their negations. And resolution is sound and complete propositionally. And what we said was this whole thing can be, and this is the only one rule, right? And this is the really beautiful thing, that if you want to perform.
Sir?
Yeah, sorry?
Sir, the board is not, the writing on the board is not very clear.
It's not very clear, okay. Yeah, this is the problem with this pen, I think. Okay, let me try again. Find black if this works. Okay. Yeah. So, in any case, I think this is, we have gone through this before, so that you can, I don't have to rewrite this. So, the idea of refutation is you negate the goal formula, convert it into conjunctive normal form, and then you have a bunch of clauses, each clause standing for a conjunct, and the clause itself is actually a disjunction, which is what you write in this set notation. And what you have inside are literals. Atomic formulas are their negations. And the resolution rule is you take a clause, take two clauses. If you find one of them occurring positively in one and negatively in the other, you combine the two clauses. You throw away that and that's it. This is the idea of resolution. You keep doing that, applying that repeatedly until you get the empty clause. Empty clause says that you have arrived at a contradiction, and then you have performed the refutation. It's sound and complete in the sense that if the given formula was unsatisfiable, you will come to an empty clause. This will terminate and come to an empty clause. In general, if you start with a negation of whatever formula that you began with, you started with not alpha and end with an empty clause, it is unsatisfiable. So, this is the idea of refutations. Now, for first order resolution, which I hope this, you lift this thing, yeah, instead of two formulas you will have in general a set of formulas, right. So, first order resolution, you're going to have, just let me throw away these. One of these pens should work. Yeah. Beta, then delta, gamma 1 through gamma n. From this you derive alpha 1 to alpha m, gamma 1 to gamma n, provided there exists some substitution sigma such that, so let me put this as not delta, yeah, delta sigma. This is what it says. If I can find a formula, a common formula here, right? You pick a formula beta and a formula not delta, and if you can find a substitution under which these two are a contradiction, right? Beta sigma is the same as delta sigma, therefore what you have got here is beta sigma and not beta sigma, and therefore you can resolve, throw away n. So beta and not delta are unifiable is what you are saying. They are unifiable means there is a common instance under some substitution. So, and how do you get to this? This is because in the first order case, what you do is you start with the formula and you Skolemize the formula, right? And this is the, so for first order refutation, again, you start with negation of goal formula, assumed to be in negation normal form. You pushed all the negations inside. Then the important thing, Skolemize. By Skolemization, what do we mean? Well, you look at the leftmost occurrence of the existential quantifier, right, the first existential quantifier in the formula, and if there is no preceding universal quantifiers at all, you replace it by some constant symbol c that doesn't occur anywhere, right. So that's the deal. If there are some k universal quantifiers occurring before, you replace that existential quantifier y by some f of x1 to xk. So that way you get rid of an existential quantifier. You keep repeating the process until you are through with all the existential quantifiers. So you have a formula which is only universally quantified. Throw away the universal quantifier, you get a quantifier free formula. So now you have a quantifier free formula, put it in CNF or whatever clausal form and apply resolution. Only thing is now you have to find unifier. Sigma is a unifying substitution. This is where, and so if you can find that, and this is clearly sound, this is the idea, because propositionally exactly the same thing is going on here, right? Because think of this formula here as one formula alpha or beta and not delta and gamma. We want, this is actually equivalent to alpha or gamma, sorry. If you had not beta here, right. So this is the same as not under sigma. So alpha sigma, gamma sigma, oh I should put sigma here because you have applied the substitution, right. So you are considering the formula alpha sigma or beta sigma and not beta sigma or gamma sigma, that will give you alpha sigma or gamma sigma, that is all. So you have applied the substitution sigma under which you find that these two contradict each other and you can throw away. So this is the idea. Now question is, in general, how do you find such a unifying substitution, and that is a unification algorithm that we were talking about. Remember that after Skolemizing, your formula is going to have lots of terms, right? You have introduced lots of function symbols, constants, so these terms are going to have some complicated structure. How do you find the unification. And this is what I was talking about. I took some examples and I showed last time. I will just continue from there. There is not much left except to show how this unification algorithm works. Now, so in general, you are going to start with unifying terms, right? You have to talk about unifying two terms, and then once you can unify two terms, you can talk about unifying two atomic formulas, and that is what you need here because these are all atomic formulas, right. So, how do you unify terms? And for that, so the unification algorithm finds, in general, given two terms, it tries to find the most general unifier. What is this idea of one unifier being more general than the other? This is something that we talked about again last time. So, let me remind you of these. Let me see if I can keep it here. Yeah. So, in general, if you have two constants a and b, they are not unifiable. If you have some f of x and let us say f of a or even f of x and h of yz, they are again not unifiable because this two function symbols are different. There is no way you can, it's only a variable that you can substitute by a term. That's the only way you can unify two terms. So, the example I took last time was this g of x and g of y. Yeah. Now, these are two terms. Clearly, you have one unifier, namely y replaced by g of x. We use this ordered pair notation, right, for substitution maps, and this is clearly a unifier, but there are a lot of other unifiers, right. The example that I took was x is substituted by 3 and y by g of 3. Now, what we would like to say that this theta is more general than theta prime. Because I can write theta prime as what? Theta composed with x replaced by 3, right. You take y substituted by g of x, and in that instance g of x you substitute x by 3. So, in general, theta prime is more general than theta if there exists some substitution sigma such that theta prime equals theta composed with sigma. Yeah. So, okay, I mean compositions of substitutions gives you substitutions, and so you can talk about this idea of one being more general than the other. And in general, you will also, I mean, it should be easy to see that g of x is as general as g of y. So, the idea of most general unifiers is that among all these unifiers, whatever is the most abstract term that you can think of, right. Now, that's not unique because you can always do variable renaming. Yeah. So, g of x is as general as, so according to my definition, you will have to write g of x is more general than g of y, and g of y is more general than g of x. I mean, this is just a way this things happen to be defined, but like I said, we usually say greater than, less than, and say greater than or equal to. So, this more general or equal to is the term that we have in mind, is the expression that we have in mind. So, with that we have this idea of, and this in resolution rule what you will do is you will use sigma as not just the unifier but as the most general unifier. This is how you do it, and so basically up to renaming, that will give you one particular. So now, yeah, and it should be, well, it's a easy proposition. If theta is, well, I have not written the definition, but I hope you remember it. Nothing much. If given any two terms, theta is a MGO of T1, T2 if T1 theta equals T2 theta, and for all sigma such that T1 sigma equals T2 sigma, theta is more general than sigma. So this is the natural definition of most general unifier that you can think of, and so that's what you want to find. And it should be easy to see that if theta is an MGU of T1, T2, and oh, I'm just rewriting this. Let me skip this. Not important. Yeah. So now it should be easy to see that if x occurs in T, then there does not exist any theta such that so this is something important to keep in mind. Why is this true? Well, if it did, what will you have? X theta would be a subterm of itself, right? I mean, for instance, suppose, I mean, I'm saying fx and fx are not unifiable, because if you have, suppose x theta is u, then f of x theta would be equal to f of u, and we will want u equals f of u equals f of u equals f of u, and so on, right? And we don't have infinite terms in our syntax, right? So this is not possible. So the unification algorithm mainly is to check whether, when you are trying to unify two terms, right, and I've got a variable x and I'm trying to substitute it by a term t, and x already is there, then you have a problem, right? So you just have to make sure that this doesn't happen, and pretty much that's all that is needed for the unification algorithm. Now there are, in general, whenever you're trying to unify two terms, there are lots of possibilities, right? You can have a constant or a variable or a function symbol, some complicated term. So here again the other one can be constant, variable, function symbol. So there are 9 cases that you have to look at, but most of them are trivial, right? Because distinct constants cannot be unified, distinct function symbols cannot be unified. So it's only a variable that can be unified with something, and here these two must be the same function symbol, so you must recursively go inside and check for unifiability. That's really all you have to do. So, and in the case of when you're, so the only cases that you have to consider is unification of x and some term t, right? You have a variable and any one of the other ones, and then unification of two terms where they have the same function symbol, right? Okay. In the case of x and t, first x is not equal to t, you can't have the same thing. Well, if x does not occur in t, then has no effect, right? And so you can x with x replaced by t is nothing but t, which is the same as t with x replaced by t. And if x does occur in t, then no unifier exists. Okay. So, in this particular case, that you just have to do the occurs check whether it occurs or not, and otherwise you can simply take the pair. If you have two terms T1 U1 and T2 U2, so if you have got a pair T1 T2 and some pair U1 U2, right, then if you have unifier theta here and, or let me say theta 1 theta 2, then compose theta 1, this unifies T1 T2 with U1 U2, right. And of course, if any one of them when you try to unify, if it fails, the whole thing fails. Yeah. So in general, your terms may not be unifiable. So you have to do, that's all. And so one thing that we usually do, I'm saying with pairs, it's actually m tuples. In general, you have to terms. You'll have to look at m tuples of terms and do this. So you do pairs at a time, unify, and lift it to sequences. Now, usually what you do is before you looking at when you try to unify T1 and T2, you rename variables in one of them so that there is no clash before you start doing it. And that's something that you can always do, and it's something that's useful. So let me take a few examples and show you the way it works is fairly clear. So let's say that, so example 1, you have got f of x b, f of a y. Now, the way I said it is that this is the pair, right, T1, T2 and U1, U2. So first, now, of course you can try it in parallel, and nothing is stopping you from trying it in parallel, but you have to follow something, and I am going to follow the left right ordering. Okay, so first I unify and I get x, for x the substitution a. Now what do I have? So, and I have to apply that substitution b with x, that is the pair that I look at, and this gives me the pair by. So that gives me the substitution, and that's the correct thing to do. Yeah. So I'm just saying this algorithmically, this is how you would do, right? First T1 and U1 you try to unify, T2 and T1 U1 T2 U2. That's how I've written it. So first the first one gives you the substitution x replaced by a. Apply that to the term here b. B with x replaced by a is nothing but b. Y with x replaced by a is again nothing but a. So that gives you the substitution. Yeah, is it clear? I'm just following that systematically, right? In general. So what about this one? F of xx and f of ab. What will you get now? As first step, x is unified, x and a are unified, you get the substitution. Now you have to apply that. You will get x with x replaced by a, and b with x replaced by a, and this will give you xb, and that's, yeah, because what you will get is ab. This is a pair that cannot be unified. Yeah, you have first get the substitution a for x, and the second one gives you the substitution b for x. So therefore you must unify a and b, which is not possible. So the algorithm fails and says these two are not unifiable. Is it clear? The same thing will work if you go right to left also. I mean, it's just that I am following a particular ordering. Yeah. Then, I mean, the way I have done is you do theta 1 first and then apply that to theta 2, and what you get is the unifier. My composition proceeds left to right. So, here is another. So, this will get more complicated as we go along. So, let us say these are the two terms that I am trying to unify. Function symbol has to be the same, right? Okay. So, first what I get is x and y have to be unified. They are two variables, so not much to do. But now what do I, the next step I am going to get g of y with x replaced by y and x with x replaced by y, right. So, I will get g of y, y. So, that says I must substitute here, and now it will fail because the occurs check, right. Remember that when you are trying to unify a variable with a term, if that variable occurs in it, that will lead to an infinite term, which is not possible, right. So, these two terms are not unifiable. Okay. Now, that is precisely why the order in which you do these things also can make a difference, but it is sound here. On the other hand, suppose the formula was fxx and fygy. Yeah, I have actually, this looks the same, but you see that now there is a difference. So, first I substitute x by y, and I am now supposed to get x with x replaced by y and g of y with x replaced by y, and what do I get? Yeah, once again I will get y and g of y, it will fail. On the other hand, yeah, okay, these two proceed identically, but you see there is a difference. Suppose I had renamed this, renamed the variables here. Here for instance, I had written it as f of x g of y and f of y prime x prime, right. Now, all I have done is taken the variable, and now this renaming of variables, right, will actually help, because what will happen, x, this will give me the unification x with y prime, and now I am going to have g of y with x replaced by y prime and x prime with x replaced by y prime, and this gives me a cheerful, no problem at all, and you will get a x by y, x prime by g of y. So, doing variable renaming before will help here. On the other hand, here if you look at it, no amount of variable renaming will help. Because remember that these two have to be identical, right. Once these two have to be identical, whatever you do, somewhere you have to, if you rename here, you are going to have y prime g of y prime, right, and that is going to, because once these two have to be identical, the occurs check will ensure. So, this is going to be always fail. So, that is why it matters. This thing is subtle, right. So, one should be careful about how we do the unification. Any question related to this? Okay. couple of more. This is going to get a little more hairy now. F of okay, G of W A H of W with G of F of X Y X Z. Okay. So in the first step, you're going to get the substitution W with F of X Y, and using X and A, you will get X with A, because this substitution makes no difference here, and so you will get X with A. And the next one, I'll get H of W with W getting Fxy, and okay, in this I'm going to get X with A. Remember that this is composition, yeah, and similar, now you will have Z with W with Fxy, and on this X with A. So doing all of this, what are you going to get here? You're going to get Z here and H with F of AY. Yeah. So, and that's the final one that you get. And the same thing, I'll just change it just a little, and you see that again there is a big difference. So let me take the same term, G W A H of W, and G, this time I have F of X Y X and not Z but Y. Okay, so these are the two arguments of the first one here, and this one is as before. Now what are you going to have? I'll get W with F X Y, and in the second step I'll get X unified with A, and now I'm going to get H of F of A Y and Y, and this will fail because of the occurs check, right? So, okay, all this is to illustrate that this thing of saying that, okay, if you find a substitution that unifies both the atomic formulas, remember that when you are unifying atomic formulas, what should you be doing? You have a sequence of terms here, right? And you have a sequence of terms here, and you must unify. So find a unifying substitution for all of these. That's why this. And my point is that whether they are unifiable or not, that there exists sigma when I write, right? That's a tricky enough thing, right? So now in general, when you have two terms T1 to Tm, you apply this recursively. So T1 through Tm, m greater than 2. First compute of course if it exists, and then recursively compute MGU of theta. So T1 theta is the same as T2 theta, and from there now you, and at any time if it fails, the whole thing fails, and this is really the this is pretty much what Herbrand did, right? Herbrand in his thesis that I was talking about gave pretty much this unification algorithm, though Herbrandt's development and treatment is very different, but this is a more modern one, and this is more or less how Robinson gave this in his where he proposed that resolution as a rule for first order inference. And for the algorithmically minded, it's this, you should actually set up the recurrence and solve and see that it takes exponential time. And so it's not a very good algorithm. There are much cleverer algorithms that exist. In fact, there is an algorithm due to Martelli and Montanari. There is one by Mike Peterson and somebody else. Vikram, do you know? Venkatesh is also there. So I don't know who any of them know. Peterson and somebody else, the unification algorithm. So these are both linear time algorithms, in fact. And one of the very nice things to note is that almost none of these linear time algorithms are implemented. They're extremely complicated and involve a lot of processing. I don't know why, but all the tools that I know of all implement the very naive unification algorithms, but they seem to work reasonably well. But yeah, there is, so now, okay, so this is the unification algorithm, and as I said, now you have the unification rule. So you start unifying clauses, right? And so let's just get to clauses. So for instance, you've got yeah, and you will see how unification actually plays a role in the inference, right? I mean, that's the important thing. Suppose you have this formula, and let's see, this is what you are trying to prove, that it's valid. And of course, it's valid, right? If there exists a y for all x such that Rxy holds, then of course for every x there exists a y such that Rxy holds, right? Whatever it is, y is the mother of x, right? If there is a universal mother, then everybody has a mother. And so this is the sort of thing that, and you let's just simply separate these as clauses. What will you get? So here is one, not or, so I might as well put it as, yeah, you have to write this and the negation of that, and the other one will have, there exists x for all y not or xy, and then I scolomize, I will get Rxa here, and I scolomize here, I get not R Vy, and this is the first thing that we saw. Yeah, you can resolve this immediately because there is a unifier where x gets b and y gets a, and you can unify these two and say that there is a contradiction. So it's what you would expect. Now let's try the other way. Suppose I try to show that this is valid. Now, of course, it's not valid, right? This is not a valid formula. If for every x there exists a y such that Rxy, it doesn't mean that there exists an x such that, right? So if for instance x you think of as the minimum, you can always say that for everything there is one that is below, but there need not be a single one, okay? And so now what will happen? Again, you have this formula for all x Rxy, and you will have for all x there exists y not Rxy, and when I scolomize, I am going to get R x fx here, and I get not R x g of y y. Yeah. No, x g of x. Yeah, sorry. Yeah. What have I written? No, sorry, I screwed up on writing my. Yeah, this is there exists y for all x, and so I should get for all y there exists x. Sorry. Yeah. So now when I do, I will get not R g of y y. Yeah. And now certainly you have a problem because you try to x with g of y and y with f of x. What will happen? Right? You will get x will get f of g of x, and y will get f of g of y, and no way are these unifiable. Right? So this kind of what I am pointing out is that this kind of inference that we do intuitively, right, arguing that in this, right, look at this. How do you say this is valid? Well, take any model, suppose that it makes this true, right? That means there is a single element A that you can find that works for all the elements here. Therefore, whenever I pick any element, that single witness that I found suffices. On the other hand, when I take a model, if I consider a model, right, if it makes the left hand side true, then for every A there is an element B, that B may depend on A. So you can't find a single element that works for all of them, right? Now the argument that you are giving here is exactly what scolomization is doing for you. And my point is that in the presence of scolomization, it is unifiability that captures what you need in. And what is amazing is that what works in this simple example is what works generally, right? By repeatedly just checking unifiability and throwing out clauses when you can, you actually build a refutation procedure, and that's in some sense the genius of Herbrand. Herbrand's theorem was to point out that you can always do this in general, right? He didn't have resolution as a rule, but this is what I would call the modern version of what Herbrand did, but that suffices. Maybe I don't want to go too much further. I'll be halfway. Huh? Okay. Now, theorem provers use, like I said, resolution is the only rule, but actually it's not quite true. There is some simplification that you actually need to do. For instance, this renaming of variables is very important. If you have different clauses, remember they are all implicitly universally quantified, right? So renaming variables is not going to make any difference at all, and this is all part of the kind of validities that we had right in our first problem set, right? So now if you have something like this, p of x and not p g of x, right? If I rename variables, let's say any one of them, this will fail because of our curse check, but this will actually go through, right? And remember that semantically these two are the same. So it's important to rename variables across clauses before you proceed, and this is something that all your theorem provers will do. Because remember now x can be unified with g of y, x cannot be unified with g of x, right? So the applying this rule works, right? It's sound, but you want it to be complete, you have to make sure that or during the unification algorithm you have to take care of these things. I just gave the thing for arbitrary terms, right? If they come from different clauses, how you handle and all you have to keep track of. That's more messy. The simpler thing is to, like I said, standardize variables apart, right? This is one thing I said for pre-next normal form, right? Once you have a formula, you make sure that every universal quantifier, if you have there exists x, that's the only one that binds x. Then if there is some other for all x, you rename it to for all x prime, etc. Right? So you can standardize variables apart, and the corresponding one in clausal form is to make sure that there is no clash of variables at all. And the other one is a rule that is normally used, and this is called factoring. This is also important. Basically, when you have a clause like this, yeah, right? Now you can apply unification within the clause. What is stopping you from doing that? Because if I apply unification, I will get PAB, this clause, yeah. If you write PXB or PAY, right, you can always make that true by making PAB true, right? You are saying either x equal to A or B equals Y for PXY to be true. So you can always make that true by making x equals A and Y equals B, right? So this is logically weaker. But remember, in Skolemization, we are always interested in preserving satisfiability, preserving unsatisfiability, if you will, right? So remember that in general, in Skolemization, we'll change the meaning, right? I've said this several times. I hope you don't forget that, right? PA implies there exists x, PX is a valid formula. But when I scolemize, I'll get PA implies PB, which is not a valid formula, right? So it does not preserve validity. So you're not interested in preserving validity, you're only interested in preserving satisfiability, so this is okay. Yeah. So factoring is something, so the rule formally stated is if I have got two clauses alpha 1 through and beta n, if there exists sigma such that alpha 1 sigma equals alpha m sigma. So there is some unifier for all these clauses, right? So throw them away and you just have alpha 1, beta 1 through beta m sigma. Apply sigma 2, right? So unify them. So this factoring is something that is used in all theorem provers. So resolution, so one thing that you do is you do the processing that I said, standardizing variables apart, and you apply resolution repeatedly and also factoring. Factoring, and the other one that you do is delete redundant clauses. And this also you should be able to see is relevant. So for instance, suppose I'll say this for propositional resolution. SR if you have got something like this, right? Now from these two I will get PR and then PQR. Surely this is a subset of the other, so you can get rid of the, yeah? A or B is stronger than A or B or C, right? So you can get rid of the bigger one, right? And this is a rule that is called subsumption. And that's another. So in general, you say that C subsumes D if there exists theta such that C theta is contained in D. I've only done it for propositional, but with substitutions you can do that. So the idea is that Px subsumes what? under a substitution, this thing is actually contained in this, because these are disjunctions, right? And therefore it's important that a smaller one is what you want. And this is very important because you can have unit clauses sitting somewhere, right? So you can get rid of large number of clauses. So these things are actually humongous, okay? So in general, the search space is huge when you work with resolution, first order resolution, so theorem provers use many such. So factoring and subsumption are the more important ones that I wanted to mention. And yeah, I have some examples illustrating these, but I don't really want to go into this. So the point is not so much to go into how theorem provers work, but to show that starting from Herbrand's theorem, you can come up with a very neat and very, very simple idea, and that works as a first order inference principle. Now, there is another one which I'll just mention here, but it's really an exciting topic, and that is, so you combine this idea of resolution or DPLL kind of procedure. Basically, you convert things into clausal form and apply resolution with factoring and subsumption, except that, okay, this is, you don't want to do it just for validity, right? This is for refutation, I said. You start with a goal formula, deny it and show that it's unsatisfiable. That shows that the formula is valid, yeah? So, but you are not interested in just showing validity, you are interested in consequence, right? You have some gamma on the left hand side, and this is what you are really interested in, right? So you have some theories, right? What you would like to show is not satisfiability of your formula, which is sort of thing that you are doing. In DPLL, you are looking for satisfiability, right? You produce a model. Now, here you have some assumptions coming, and those are theories, right? You want to operate within a theory. You have some axioms of some theory, and within that you want to do your DPLL or resolution. So this thing is called satisfiability modulo theories. I'll just show you how it works for a very simple example, and then you can see that theorem provers can actually build this into the background. So these are called, exactly like SAT solvers I was talking about, these are called Smt solvers. So that stands for satisfiability modulo theories. And the idea is very simple. You're going to bring everything down to literals, right? Atomic formulas and their negation. Sets of formulas of this kind is in clausal form. Except that the atomic formulas that you're going to work with are going to be interpreted within theories. This is the idea. That theory may be some arithmetical theory, so your theorem prover has whole lot of things that you have already proved as lemmas, theorems, right? Now apply those theorems and use them to keep reducing your clauses. That's the idea. So this is the idea of satisfiability modulo theories, and that's very powerful. So today Smt solvers are the things that are used immensely, right? And Smt solvers are available for any number of mathematical theories that you can think of. Huge amount of group theory, theory of rings, theory of fields, various kinds of theories. There are Smt solvers, geometric theories. So Smt solvers exist for many theories. So I don't want to get into that, and that's like a big subject in itself. But just to give you an example, so for instance, suppose the atomic formulas that you have ended with in clausal form are these. So I am going to use an order theory on integers. So 2a less than b, b less than a, 3a greater than 2, a less than 0, c not equal to 0, okay. So this is a clause that you have, something in clausal form you have arrived at, and the atomic formulas are all of this kind. They are just order and equality, inequality, and this is what you would expect in negation normal form when you push. Now suppose this is a unit clause, right? Remember that when we talked about DPLL we mentioned. So there is one here, so that I can propagate, right? So I can propagate B less than A. Basically I take conjunction of these with the others and see what happens. So that will give me, yeah, so first this will get knocked out and I will get 3A greater than 2, A less than 0, and then the other one. Where is, oh, I have forgotten that, huh? C, oh, acha, this is not C less than 0, C equals 0. I mean, there are no meanings, it's just cooked up stuff. I get that, and then I get, yeah, C not equal to 0. Yeah. So B less than A is resolved at not B less than A, and I get only C not equal to 0, the other things come here. Yeah. So this is just resolution, and now I have C equal to 0 and C not equal to 0. I resolve, and I will get, what do I get now? 2A less than B and 3A greater than 2, A less than 0. And now, yeah, so is that, yeah, this is it. Now at this point, okay, there is nothing to resolve here, right? So far I was applying resolution. Now this is where the thing starts using the theory, right? First it gives a model, it tries to, so it has, it takes either this, it takes this conjunct has to be made true, right? So I take 2A less than B and then try to build a model with so I get B is less than A and C not equal to 0, yeah, and 2A less than B and, well, one of the two, right? Let us say it takes 3A greater than 2, yeah, and then it gets a contradiction, yeah. Now because now you can apply the theory and you can say that you can't have 2A less than B and 3A greater than 2 and B less than A, right? You just propagate that because you're going to get 2A is less than B and B is less than A, therefore 2A is less than A. If 2A is less than A, you can't have 3A greater than 2. Now this is something that it gets not from resolution but from the theory, right? It applies the theory as a lemma and tries to prove that within the theory and says no, that's not possible, and therefore it gets the other model B less than A and C not equal to 0 and 2A less than B and A less than 0, okay, and this is okay, yeah, and this is actually a model and it's satisfiable and it says okay, it's satisfiable. This is to, I mean, again, this little example hardly does justice to SMT, but to tell you that this combination of using DPLL or clausal resolution, bring it to clausal form and reason about atomic formulas in the theories that you have got, that your theorem prover has got this vast knowledge of all these things, right? So these are all things that it can actually show it's not, so it's just atomic formulas, right? And it's just a conjunction of atomic formulas, right? So that's why it's able to directly try to prove it within the theory. There is, and this is just the so-called conjunctive queries, right? Conjunctive queries can be conjunction of literals is something that you can quickly check, and therefore you do that. So this has turned out to be a very important development, and as I said, current technology, if you look at, it's really Smt solvers and Smt solvers. That's really what a lot of this thing is. So every year, in fact, there is a SAT SMT school in India. I think last December it was in IIT Bombay. This December I don't know what's going to happen, whether it will happen or whether it will be an online school or whatever. Every year there is a SAT SMT school. There is Srivas Mandayam and CMI who has actually built Smt Solvers earlier. So there are a few people who work on Smt Solvers in India. I don't know too much about it, but all I know is that there's a lot of what I would call logic engineering work that goes on in this line. Now, there is one topic that I want to mention, and I should do that in whatever time left when Meerda is here today, because this is to talk about certain branches that we have not followed, and that actually is very relevant to the current discussion. Okay. Okay, so this is something interesting, and this is this idea of what are called logic programs. Where you want to take statements in logic, statements in first order logic is what we are talking about here, as specifications of programs. And in fact, the jargon is treat formulas as executable specifications. Executable documents we talk about, so why not executable specifications? So look at something like this. Here is I say y is even, let me write this as a definition. If y is 0 or there exists x such that y is equal to s of x standing for successor of x and not even x. Yeah. This on the right hand side is a first order formula. It's a first order formula in the vocabulary with equality and one function symbol successor and one unary predicate symbol even. But this is actually defining a formula called even y, right? We don't have definitions in first order logic, but you take first order logic and strengthen it with definitions and you get recursive definitions, right? The moment you strengthen first order logic with recursive definitions of this kind, you can think of this as a program. What is this program? The program is to check whether a number is even, right? It says to check whether y is even, it suffices to check whether it is 0, or you can find some other x such that y is a successor of x. What does that mean? Well, you gave me the number x, right? So I look at x plus 1, right, and check whether that one is even, right? And if that is not even, then x must be even, right? So either y is 0 or the successor of x is actually not even. If that is so, I certify y to be even. So this gives you a way of checking whether the the specification of the predicate even can be thought of as a program. Now, only thing is, how do you give meaning to such a thing? Now, if I can write a formula like this, I can also write a formula like this. Yeah? Was there a comment? Okay. Here, let me write one more. Y equal to 0 or there exists x such that y equals successor of x and even x, or in fact I will write successor of y is even. Look at this program. I could have just written this. Y equal to 0 or successor of y is even. Y is even if y is 0 or y plus 2 is even, right? This one says or y minus 2 is even, right? Y is even or y minus 2 is even or y plus 2 is even. I am just trying to point out to you that there are many ways of checking whether a number is even, right? Who says that there is no one single program to do this job, right? Now these are all specifications, if you like, but they can be thought about as executable specifications, and this is the interesting idea. And this is the idea of logic programming. Logic programming, typically it's not written in this first order form. The way you would write it is you would write it as, for instance, even y. So you will write it as a collection of clauses. The clauses are written as even 0. Sorry, this pen is not good. As usual, I screwed up with some. Even 0. This is one clause. Even y provided so the programming language Prolog, you write it as clauses of this kind. This is a clause which doesn't have any, so this you treat it as conjunction, right? This is y equals sx and not even x implies, in fact, in Prolog you don't even write it like this, you write it like even successor of x. So then you take any given number which is always going to be of the form successor of m is represented as successor to the m of 0, right? That's how it's written for m greater than 0, and then you unify. You take that and you unify with this, which will give you something like this, and you keep going down and you find even of 0 and you stop. So this is the idea of logic programming, and in general you will have, and this one for instance would be written as the second one, even 0, even successor of x if even x. You could have stopped here, but this one also says even x yeah. These are all disjuncts, right? This is what is called a definite clause or a horned clause. The general form is m greater than or equal to 0. If m equal to 0, you treat it as a fact. If m is greater than 0, you read it as if b1 and b2 and bm hold, then a must hold. So in general, now when you want to compute something, so that's given as a goal. So you take this goal, try to unify with, and a program is simply a set of clauses of this kind. So program is a set of clauses C1 through Ci. But these are not the general clauses that I talked about, these are horned clauses. Don't worry about the particular terminology, but so when you start with a goal, what do? Well, you deny it. So that is of the form G implies nothing, so you write it in this form, and then this is basically the idea of resolution. So then try to unify with any one of them. That will so that you think of as a goal, that will generate sub goals, right? If it unifies with A, to check that A and G unify, you have to go to, so that will give you some theta. So that will generate sub goals B1 theta to Bm theta. Recursively keep on doing it until you find the empty clause. So this gives you but this, it says it's provided, right? It's in one direction, but you can take all of this, you can see that logically this is the same thing. So in general, you can talk about taking first order formulas and writing recursive definitions for some of the things. Now, when you were trying to, in the assignments that I gave in the first one, I think, when you try to write down first order formulas for some of these things, like for instance, you want to write a graph as bipartite, right? or some of these things, it would be very nice if you had recursive definitions, right? Once you had recursive definitions, you can actually write many such specifications. I mean, for instance, Euclid's algorithm, right? We are all used to writing. So GCD of M and M, GCD of Mn is M minus N, GCD of M and N is A if M greater than N, and GCD of M minus N, N is A. GCD of M is GCD of M, N minus M, A. And that's a Prolog program, a logic program, because this is certainly true, right? If M is greater than N and GCD of M minus N and N is A, then GCD of M and N is A, right? So this gives you a recursive definition. And now, as we very well know, once you have recursion, this whole thing can be lifted, and in fact you can prove that if you just have logic programs like this, you have to give semantics somehow, and like what I am saying is that you have to give semantics for this little programming language using resolution, but if you do, you can in fact show that this is complete. It's universal in the sense that all computable functions can be computable relations, because these you are working with relations, actually can be computed using this programming language. Now you ask, okay, that's all fine, but what exactly is going on? Because in first order logic you don't have recursive definitions, right? What is this enrichment of first order logic with recursive relations? What does it actually give you? How do you give semantics for this? What are models for these things? And there is something very interesting. Maybe in the next lecture I will give this in detail, because we don't have time to start this whole thing and do it today. But let me just give you the idea of how you give semantics to these. This is something that was recognized by Kleene very early. And what Kleene said is that if you want to talk about computable relations, well, I know that not everybody here has gone through theory of computations, so I don't know where you are. Ananya, in theory of computation, have you guys come to Turing machines and okay, you're not yet got to Turing machines. So notions like computable relations, recursively enumerable and all will come later on, and so let's not worry too much about it. Think of it as, here is a program for even, right? You think of your atomic formulas as program names, right? Even is a program, right? That's an atomic formula that you are defining. Anything that you are writing on the left hand side, you think of it as a program name, right? Or a subroutine or something like that, right? So now these logically you can think of them as being true or false in a model, right? But now because of recursion, in general, you may not be able to determine whether it's true or false, because in the process of doing so, you may get into a loop, right? To try to solve this, you generate a goal like this. To do that, you generate one. You keep on doing this and you may never terminate. It's very easy to find, something where you don't. For instance, suppose you didn't write this, right? And you just keep going. You can keep trying to check and keep going forever, right? So Kleene suggested that if you want to think about computation within logic, right, you should go to a logic which has not 2 truth values but 3 truth values. So think of them as success, failure, non-termination. These are the 3 possibilities. It's not so much about truth and falsity. I managed to succeed, right, in trying to solve the goal, right? I try to unify and I managed to succeed, or I fail because there is no unifier, right? These things all come out and say, no, I can't proceed, I fail, or you go on forever. These are the three possibilities. So think of this as true, false, and a bottom to denote undetermined. So the three truth values that Kleene suggested was that you think of this as known to be true, known to be false, and I am not able to determine whether it's true or false. That's what recursive definition brings. So you start with first order logic where you have your formulas and you can give you have a notion of model, and the notion that we work with is exactly the same as what I talked about last time. You start with your set of clauses, right? You have your set of definitions if you like, and look at the Herbrand base. What is the Herbrand base? You remember, you take all the terms mentioned in the formulas, take the constant symbols, build a Herbrand universe, right? And take the atomic formulas here. For instance, here, what will be the Herbrand universe for us? 0, successor of 0, successor of 0, and so on. That's all. That's a Herbrand universe. What is the Herbrand base? Even is the only predicate that is there, right? So even 0, even successor of 0, even successor of 0, and so on. So that's the Herbrand base. Now what is the Herbrand interpretation? Any subset of this, right? Now you hope that the Herbrand model that you are looking for will have even 0 but not even successor of 0. So that's okay. The particular model that you are looking for is even of n, where n is actually happens to be an even number, and that's what you want to show is a Herbrand model of this, right? Now in the process of constructing the Herbrand model, you may get into an infinite loop, right? This is the point. So what Kleene suggested was, for doing this, enriching this with recursive definitions. I mean, Kleene didn't say that. Kleene said something different, but we are paraphrasing Kleene. Okay, and so you can work with the three-valued logic, where truth and falsity are as before, but there is this idea that in the process of determining truth and falsity, you may get into a spin. So you have a third truth value, and this is the idea of non-classical logics with non-classical truth values I never talked about. This is as good a time to talk about it as any other. And so you can give semantics based on a three-valued logic, and you get an amazingly simple and beautiful semantics. And in the process, so next time, as I said, I'll take it up. So what we will do is to give semantics to logic programs using Kleene's three-valued logic. And Kleene's three-valued logic has some, so now you've got three values, right? So what does negation mean? Well, negation of true is false, false is true, bottom is bottom. This is what you would expect. What about conjunction? Well, true and true gives true. Okay. Now, and this is Kleene's special proposal. So, you can differ on this. Now, with respect to the classical truth values, they behave exactly as before. Okay. If any one of them is false, the conjunction is false, right? So that's something that you preserve. Yeah. But then if one of them is known to be true and the other one is undetermined, the result is undetermined. So this is Kleene's three-valued logic. But of course, there are lots and lots of possible three-valued logics. What I am trying to say is that the notion of logic programming specifically corresponds to Kleene's way of doing logic, and this is conjunction. So you can think of how you would give semantics for disjunction, implication, quantifiers, whatever. For quantifiers, we are going to follow the same thing that we talked about. As I said, we are working with Herbrand base, Herbrand models, and you just try to construct Herbrand models. In the process, what, as I said, I will do next time is that we will change our notion of basic models itself slightly differently. So instead of working, so far what we have been doing right from the beginning was I introduced this notion of formula alpha being true in a model, and this is a truth definition due to Tarski, and this is what we have been working with, and this is the only thing that we have done so far throughout, and that leads us to notion of logical consequence, all this. But there are also other theories of truth that logicians have looked at, and there is another one which is Kripke's theory of truth. It turns out that the idea of logic programming which came out of this, and as I said, which theorem provers have been built on using refutations, works with Kleene three-valued logic and Kripke's theory of truth. In Kripke's theory of truth, you don't work with models at all, you work with partial models. Exactly like you don't have just true and false, right? In models, what is the idea of a model? Every formula it will make either true or false. In Kripke's theory of truth, a formula can be true or false or have no truth value, right? So it's possible for your interpretations to be not maximal in the sense that your interpretations are partial. So this idea of working with partial Herbrand models and Kleene's three-valued logic gives a very beautiful and very simple semantics for logic programs. So, and this is the extension of taking first-order logic and throwing in this idea of recursive definitions on top of that. And of course, we don't have the machinery to prove that this gives you universal computing power. It's exactly as it gets you Turing computability, what ordinals you get to, etc., etc. That's more complicated. But what is very nice is that with Herbrand models, you can build, as I said, with partial Herbrand models, you can give semantics of logic programs and give meanings to computable relations, partial recursive relations, etc., in a fairly neat way. So the main idea is that what you do is with every formula, you associate an operator. The idea is that the operator takes something like this as input and produces. You are partially you have determined something for even. For instance, you know that 0 is even. Plug it in, that tells you 1 is not even, right? Plug it in, it tells you 2 is even. Plug it in, so it keeps building up the semantics, right? It starts with even 0, this is what we had. It starts with even 0, takes that as input, from that determines 1 is not even, and now it takes as input 0 is even, 1 is not even, from that it determines 2 is even, and so on. It keeps going, and in the limit it gets this set even 0, even 2, even 4, and that's the Herbrand model of this formula. So this computation is realized as a fixed point of an operator, and that operator is working on a structure of this kind. So it's quite a nice algebraic structure, and so we'll talk about that next time. So I'm not going to again do too much of logic programming as such, but just to show this connection between logic and computation in a very simple fashion. And what is also very interesting is that it also leads us to various other interpretations that you can have, and one very simple interpretation is going from 2 truth values to 3 truth values, right? And we don't have to mess with three-valued logic at all. As I said, working with partial Herbrand models does the job for you, and this idea of associating operators with programs is also something important to learn. Okay, so I'll stop here. Any questions?
Ramanayam, I am leaving now.
Yeah, sure. Anyway, I'm also shutting down. So, any questions? Anyone? Okay.